Welcome back to this second video in the series on quantum mechanics using programming. In this video, we're going to be looking at the wave function and the properties of the wave function and how it looks and how to program it. And as always, if you liked the series video, like it, share it, subscribe, and comment in the sections. That's going to drive up the visibility for the video. So in the last video, I gave you this exercise of answering like, what is the square root of -1? It's sort of a basic exercise at this point. And how do you calculate with the square root of -1 in Python? Now, the square root of -1 is I, and we're going to get what that is, but it's an imaginary number. And then how do you calculate with the square root of -1 in Python? So I'm going to go to my Colab script here, and I'm going to import numpy as np. So I've already installed confit here, which we're going to be using for our simulations later on. So if I write like x or a is equal to the square root of -1, I'm getting something invalid because it doesn't know how to do that. But to calculate with the imaginary number I in Python, you actually write j, except you cannot just write j because j is going to think of that as an integer, so you write 1j. And so if I write a is equal to 1j, then a is I. And so if I do a squared, then I'm getting -1. Well, actually, it's a complex number, so it's going to show me the real part -1 plus 0j. So it's exactly -1. So that's the answer to those questions. And the reason, of course, that I gave you this exercise is that we're going to look at the wave function as a complex field. So the wave function, yes, it's a complex field. So the question is, what does it mean? What does that mean? So let's start with the notion of a field. So what does a field mean? Well, a field is something that has a value at every point in your system. So in this video series, we're going to be concerned with one-dimensional, two-dimensional, and three-dimensional space. So a field in that sense is something which assigns a value to each point in space. So for instance, that could be temperature, right? So in this location, the temperature is 2. In this location, the temperature is 5, etc. That is a field. In one dimension, we can visualize a field by drawing the space on the first axis. So this is the x-coordinate, and then we mark the value of the field at that position as the height over the graph. So for instance, at 2, the value is 0.2. So that's what a field is. That explains this part. And then the second part is complex. So what does complex mean? Well, it means that at every point in space, it assigns a complex number. So for instance, in this position, it could assign the number 3 plus 4i, whereas in this position, it could assign the number 0.3 plus 0.2i, which are both complex numbers. And what makes them complex is that in addition to being a normal number, a real number, they have this complex part, which is I. This might be a repetition for some of you, but I'm going to go through it, so you can skip ahead if you think this is easy. So a real number is defined on the real number line, right? So 0, 1, 2, and then all the numbers in between. To define a complex number, we add that imaginary part on the y-axis and visualize it as a point in what we call the complex plane. So for instance, the number that I had here, so this number that was 4 plus 3i in this position, gets mapped to this point in the complex plane. So its real part is 4 and its complex part is 3. So 4 plus 3i. Now this is not the only way to represent a complex number. We can also represent it in what we call with its amplitude and with its phase. And when we're doing quantum mechanics, this amplitude and phase division is actually more informative than the Cartesian real part plus imaginary part decomposition. So the polar representation is done by writing down the amplitude of the complex number. So the amplitude is the distance from the center of the complex plane to the position of the number itself. So for instance, if we're looking at this point here, then the amplitude is equal to 5, because that's the distance from the origin of the complex plane to this number 4 plus 3i. And in addition to this amplitude, we also need to define the angle with the x-axis, which is called the phase. So the phase of this complex number is 36.87 degrees, which in radians is given by 0.205 pi. Now, throughout this video series, we're going to be showing these complex numbers not as heights, but as colors. And the color scheme is always going to be the same. So the way that I've chosen to represent them in Comfit is by saying that the 0 phase, that's red. So, and the pi phase, if the phase is pi, then it's teal. So this phase here, this 0.205 pi, that's located somewhere here between 0 and 0.33 pi, which means that I'm probably going to color this phase orange. And so using this color scheme, we're actually able to plot the wave function in the same way that we plotted the wave function or the regular field in one dimension. So the way that we're going to do it is that we're going to draw the x-axis as before. Now, if the value of the field at 0 is 4.3i, then I'm going to draw the point at the amplitude above the x-axis. So it's located 5 above the x-axis, and then I'm going to color in the distance from the x-axis to that point with the color corresponding to the phase of that number. So for instance, here I've plotted the point 0.2 plus 0.1i. So what phase should that number have? Well, if I draw this number in the complex plane, I'm just going to do this really quickly. Sorry, not x. So this is real, and then imaginary. Then 0.2 plus 0.1i is going to be approximately this, is located here, right? So this angle here is somewhere like 0. I think it's probably somewhere around yellow, I think. So it's probably going to be, the phase is probably going to be around here. And so therefore I'm going to color this this distance here yellow. And if I look at this other number, 5 plus 3i, oh, sorry, that was yellow. So 5 plus 3i, yeah, it's also actually quite a small face. That's also probably going to be like orange-ish here. So I'm also going to color in this here as orange. But now you can sort of see how we are able to plot a complex function in one dimension. So there's that, yeah. And also there is an important property of the wave function, which is that if I multiply the complex conjugate, the complex number by its complex conjugate, I get the absolute value of the number squared. So if my complex number is 4 plus 3i, I multiply it with the complex conjugate, which is 4 minus 3i, then I get just the absolute value or the amplitude of that number squared, and the amplitude is 5, so we get 5 squared, which is 25. That's going to be important later on. So now let's have a look at some example wave functions given this representation here. So What I've done here is that I've installed Confit. I've imported NumPy already, but I'm going to import Confit as, I'm going to increase the size on my screen a bit. I'm going to port Confit as CF. And then I'm going to create an instance of the quantum mechanics class. cf.quantum mechanics. And the dimension is going to be 1, and I'm going to put the limits of the x-axis between -10 and 10. Now, what happens when I do this is that this QM instance is going to have a lot of the values and properties that I need in order to plot and visualize and do calculations with quantum mechanics. So for instance, if I do qm.x, is going to give me the x coordinates on which my wave function is going to be defined. If I do qm.dx, it's going to tell me what the spacing is on my x-axis. If I do qm.dt, it tells me what the dt is going to be. So QM is an instance of it's an object which has a lot of properties, meaning dx, x, etc. But it also has a lot of methods to do different things. And we're going to have a look at all of those things as we go along. But for now, we're going to use qm.x, which is this array of x coordinates, to plot a Gaussian wave function. So a Gaussian function is defined, it's something that looks like this. Well, almost, right? This was not looks more like an omega, to be honest, but it looks like this, and it has like a width and it has a height. And the most easy expression for a Gaussian wave function is just e to the minus x squared. So we're going to have a look at this function. This sort of looks like an alpha. So I'm going to write this as x squared. So we're going to code that first. So I'm going to create a Gaussian, and I'm going to write x of minus qm.x squared. Now, NumPy or Colab Python doesn't know what x means. It's not defined. So I need to say that it comes from the NumPy library. And when I do that, I have created this Gaussian function. Now, since x is a real number, Gaussian is also going to be a real function. So the way to plot this function using the Confit library is to use the function called qm.plotfield and then this Gaussian function. And when I do that, I get this whole thing, which doesn't look like a plot. And the reason is that this plot field function returns two things. It returns a fig object and an ax object, where the fig object is the figure containing the plot, and then the ax is like information about where this plot is located in the figure. It's sort of mimicking the matplotlib functionality of fig and ax. But the point is that if I want to display the figure, I can just write fig afterwards. And so here you can see the wave function, or this is the Gaussian, and it's a real field. It has a value at every point, and if you hover over, you can have a look at the field value as a function of x. But anyway, so this was a real function. Of course, we're interested in a complex function too. So the easiest thing I can do is I can just like multiply the Gaussian with a complex number, right? So I do complex Gaussian is equal to 1j times Gaussian, for instance. So if I do this, now I have a complex Gaussian, which is just an array of numbers, which are all complex, really. And so if I try to do the same thing as before, qm.plotfield, complex Gaussian. So this is Google's Gemini suggesting autocompletion for me. I need to spit out fig and x, and then fig again. First of all, it's going to throw me an error. So it's saying the provided field was complex, right? Which is what I did. This might be due to imaginary parts. It's suggesting something. But the reason is that this plot field function expects the field that it's getting to be a real field, not a complex field. And so essentially, it's only plotting the real part. It says like the imaginary parts will be removed, and then it just plots the real part, which is 0. So in order to actually see this function, I need to call on the function plot complex field instead. And when you do that, you get this sort of nice plot here, where you see that the amplitude is as before, but now we've colored in the region between the x-axis and the height with the value of the phase. And you can see that the value of the phase is 0.5 pi everywhere, which is 90, so pi over 2, which is 90 degrees, which is what we got when we multiplied the whole function by I. We can probably get something more interesting if I do Gaussian plus 1i Gaussian. Then I'm getting a mix of real and imaginary. And the result of that is that I changed the phase of the wave function to be orange. And I can make it even more complicated by multiplying with, if I say like the imaginary part should be 1j times the x coordinates times the Gaussian, then the wave function is going to look more interesting. So right now, here you see that the imaginary component of the Gaussian function is actually changing along the way. So now the phase is actually changing from here, where it's 0. So this is a completely real number, and then it's changing. So this is a way to visualize a complex wave function, a complex function in one dimension. Now this creating this Gaussian state is something that we're going to be doing very often in this course, and so therefore there is a function that does this for you in Confit. So if I do qm.conf initial state initial condition Gaussian, and now what it's doing is that it's creating this Gaussian function, and it's saving it into this variable qm.psi, which is going to be our wave function. And so if I want to plot this, I can do plot complex field qm.psi, and then display this figure. You see that we get sort of the same thing, except it's starting out being quite wide, actually, this Gaussian by default. We can change that by saying how wide we want this Gaussian to be. Like for instance, if I want the width to be 1, and then I plot it, then the initial Gaussian is going to be less wide. And not to sort of get ahead of myself, we can also give this Gaussian wave function an initial velocity of 1, which I'm going to be explaining in some of the videos to come. But essentially what it's going to do with the wave function is that it's going to give it a what we call a phase gradient. So the phase of the complex function is also going to change as we move along. So that was how we plotted a wave function. Now, for the exercise for the next video, I would like you to try to take this function, or like the function that I get when I do this and do qm.psi. So take this array here, and I want you to try to integrate numerically the integral of just this function from -10 to 10 of dx, and then integrate from -10 to 10 the absolute value of this function squared, and then just in the region from -2 to 2. And if you feel like If you feel like this is something that's a little bit hard, that's okay. You're not supposed to get it immediately. But the most important thing is that you try to think about it and try to make it work. And then I will go through the solutions in the beginning of the next video. So I will see you there.